If you have taken this class, it means you are doing physical chemistry or interested in it, and you're looking to describe chemical reactions or see some background behind it. So there are advanced topics which could be part of this class if there would be more time, but attendees were brave enough to pick them selecting and presenting. So it will be a complement to a class material and hopefully will help you in your future research careers. But if anyone watches on the recordings, there could be a reasonable question, or majority of audience are chemists, why there will be so many subjects in the subsequent presentations that look like physics. The background of physical chemistry and actual physics are very similar. Those who are interested in chemistry and reactions, like chemical transformations or charge transfer, deal with the same model, same math, and main challenge in this modeling that there are heterogeneous degrees of freedom, like electronic and nuclear. And the math to describe this type of degrees of freedom is very similar to what was developed in physics to describe other pair of heterogeneous degrees of freedom of electronic states and quantized light. And this is a reason why some materials which belong more to physics are penetrating into chemistry audience.
All right, so I'll be presenting about non-adiabatic couplings of the first and second order for orbitals and excitons, and there'll be some similar stuff to what Lola talked about since she addressed non-adiabatic couplings. So as for what they are, it's a coupling between the electronic and nuclear degrees of freedom. And in the case of nuclear degrees of freedom, that can relate to like vibrational degrees of freedom. And in this case, since it's non-adiabatic, the nuclear degree of freedom is not approximated as adiabatic, and I'll explain a little more about that in a moment. So why do we consider non-adiabatic couplings? Whenever we're solving dynamics of some quantum system, we like to use the time-dependent Schrodinger equation, but it can be pretty difficult to solve depending on what your wave equation is, especially if you have a lot of ions or electrons in your system. So something we like to do in computational chemistry is to use the Born-Oppenheimer approximation, which will separate the electronic and nuclear wave functions, and then the nuclear wave functions are treated as adiabatic, or essentially like it's not moving in space, its positions are fixed, and the electrons move about how they will. The advantage of using this Born-Oppenheimer approximation is that it's computationally more efficient, it simplifies your equations, and also you can like simulate molecular dynamic trajectories in a classic way. The disadvantage of doing molecular dynamics in this classic way is that there may be quantum effects you're not accounting for, like tunneling or 0-point energy. And we also like to consider non-adiabatic couplings for things like photoexcitations, because like your ions will move around and we want to see how that affects your trajectories. So to construct the non-adiabatic couplings for single orbitals, for starters, instead of splitting up the electronic and nuclear degrees of freedom, we're going to express our total wave function as a linear combination of the electronic adiabatic states and some coefficient. And if you put this ansatz into the time-dependent Schrodinger equation, we're going to have our diabatic coupling term, which is this VK, and the non-adiabatic coupling vector. And that's been explored by Lola. So in the process of obtaining these expansion coefficients, as discussed, we want to find what the probability amplitude of these coefficients are and fewest switches surface hopping, so that way you can know the probability of a state transitioning occurring between some different time steps. But then going back to finding this coefficient, you can do some renaming of how you call your coefficient and the diabatic term. We get our time-dependent Schrodinger re-expressed, and then since we want to integrate it, and we're going to be integrating it computationally, since we're going to probably be doing simulations on a computer, you can use the fourth-order Runge-Kutta numerical integration method. And in the process, this C tilde coefficient that we've renamed, it'll contain all the information, so you don't have to worry about going back to finding that C of J. And since we're in Runge-Kutta integration approximation, we get a second-order derivative. we've moved on to second order non-adiabatic coupling. We could also rename our non-adiabatic coupling vector like so. And with that, we get this final expression for the non-adiabatic coupling vector. And that can help us find what our coefficients are. And note that we have, for these electronic adiabatic terms, we have two different time steps. So if you've done non-adiabatic couplings, you'll note that you at least need two different time steps to get a calculation. So if we want to move on to excitons, which are, in brief review, it's a quasi-particle that's an electron-hole pair. It can be useful to look at electrons if you're looking at things like singlet fission or some charge dynamic situations. And the difference between orbitals and the excitons is, instead of having our single orbital exciton wave function, we use the Slater determinant basis, which will be made up of these adiabatic electronic structures, which they could be like represented as one electron constraint orbitals. So move on to that. You can express the Hamiltonian in terms of this determinant basis, and from I know this can connect to how you construct your non-adiabatic vector. And so once you have your Hamiltonian, we get this similar looking expression to before with the Runge-Kutta expression for the numerical integration. So you can solve what your non-adiabatic coupling vectors or your transition dipoles are at different time steps. And if we want to connect this all to non-radiative relaxation, since we're interested to see our system evolves over time. Like we talked about, if you have your coefficients and you know the probability of them transitioning, then you can know how many are in a certain population. So supposing you're in surface hopping, you can have your number of orbitals, or I guess exciton pairs that are in a certain state, and then you can see how the population will change over time. And I guess another item of note, in the process of solving our non-adiabatic coupling equation, we are able to symmetrize our equation, and that's an important feature since that makes the integration, it makes your system time reversible, which is important for the integration setup we do, and also having a time reversible situation is important for detailed balance. So, all right, that's my presentation. I'll leave it up for questions.
Can you hear me? Okay. So I'll be talking about how to go from density matrix to surface hopping algorithm. So surface hopping is a semi-classical method where the electronic and nuclear degrees of freedom are coupled, such that the transitions between the adiabatic states are very fast, and these are called non-adiabatic transitions. So surface hopping models these non-adiabatic transitions as an instant jump between two adiabatic surfaces, like I'm showing in the diagram. And general expression for describing this non-adiabatic dynamics is this expression I'm showing here. This left part represents time dependence, because most times when you use this method, you want to measure, you want to describe events going on with like relaxation or like quantum dissipation. So here represents the energy of the current state before it hops onto the next one. And the term here is a non-adiabatic coupling, which represents the coupling between the nuclear degrees of freedom and the overlap of two adiabatic surfaces, say K and J. Now, surface hopping actually accounts for these transitions using a hopping probability, and it uses the density, the time evolution density matrix formalism, because it helps to describe the probability of finding, because the density matrix formality helps you with probability. So density matrix is just a different form of describing the state of a quantum system, and it's useful for time-dependent problems like relaxation. So here I'm showing an expression of the density matrix operator, and kind of like analogous to the time-dependent Schrodinger equation, just instead of wave function, you're using density matrix here, and then you have the Hamiltonian. So to describe the time evolution of this density matrix operator, say you have like a two-level system, then you describe the interaction as this, and then you are able to get the components of the density matrix, which can be rewritten as this expression where L here is the Liouvillean superoperator. This kind of like this looks like the one that we derived in class, except that like we just have much more. This includes the Rabi frequency. Yeah, this includes the Rabi frequency, which comes from the interaction term V here. So how exactly do we go from this density matrix to surface hopping? So we know that density matrix can be defined as the square of the expansion amplitudes, say going from state K to J. But then, since Nonadiabatic transitions involve switching between two adiabatic surfaces and bringing back this expression here. Now, this expression can be rewritten in density matrix formation, which was done by Tori. So here, this expression is not very far from what you have here, just that it includes the density matrix representation here. And then here you have more states. You can see here it was just K and J, but then here you have L. And that's one of the good things about density matrix. It helps you to include the effect of mixed states. So here, L here represents the presence of a mixed state with K and J. So technically it's the same equation here. So typically the diagonal elements of density matrix represents population, while the off diagonal represents coherence. Now, the fewest switches method, which is the two-layer approach, actually models probability of switching between two states. So it represents this diagonal element here as a time derivative, and then this expression here represents probability of hopping from state K to L. So this expression here is defined as this. It's essentially the same thing as this expression here, just that it includes the imaginary and real part to account for the diagonal elements and the off-diagonal element of the density matrix. So in order to maintain correct populations with this method, this algorithm kind of like minimizes the rate at which switching occurs between two different states. So G here is how the probability is being defined. So this expression, showing some spread. This BJK here is this expression here, and then you have AKK, which represents the density matrix density matrix here. So if this expression is being evaluated and this value is negative, then it's zero, meaning it's not going to make the switch between the states. But then a random number, which I'm not exactly sure how to generate, how they come about that number, is being used. What's the word now? A random number is being generated, and then you compare it with this value. say, for example, if that number usually between 0 and 1, which serves like a probability, if it's greater than what is evaluated here, then it means that it's going to make the switch between state K and state J. Yeah, that's all.
Okay.
So yeah, I'm just going to be talking about the some quantum master equations. I did not have time to get into the Green's functions as a different method of doing like quantum relaxation for an open quantum system. So I guess the first natural question is, what even is a master equation? Basically, it's a set of differential equations that allows you to completely solve for everything in your system as it allows you to solve for everything in your time-dependent system. So in quantum mechanics, that usually means that you can explicitly solve for your time-dependent density matrix, because then you can describe everything. So the first one that I'll be looking at here is the Redfield master equation, where this is the actual equation itself. And then you've got this like dissipative term, where this is sort of the interaction between your system and the bath. And then essentially you're using the Redfield tensor, which looks like this. And it looks very gross and complicated, but this is actually, I think, the simplest and the easiest one to do, as far as I understand. This is the one that we usually use, like in our research group. So basically, these things are sort of like transition rates, right? So these things make up your Redfield tensor, right? So this thing describes how your system will actually relax, right? So it's called either the Redfield or the relaxation tensor. Nice things about this one is that it is a Markovian equation, right? So what that means is that you don't need to know the entire history of your system as it evolves through time. You only need to know the like the time immediately prior to the state that you're trying to solve for, right? You don't need to, yeah, you can go like step by step with it, which is very nice. It makes it much easier to compute things, you know, like in, you know, a computational field like we do. And also if the autocorrelation functions between like your states, if those decay very quickly, which they do in a lot of cases, you can reduce these to just like a single number, and they're very easy to compute. And that's usually what we do when we're, you know, doing our calculations with all the codes that we have, you know, in-house here. So that makes this a very expedient way to calculate things. You just have to keep in mind that you are explicitly assuming with Redfield dynamics that the system evolves much slower than the bath, that the coupling between your system and bath are weak, and that there is no correlation between the system and the bath at the initial time. And so the next master equation is the Lindblad master equation. And so this is essentially like a framework to generate like Liouville operators. Because as far as I understand it, these can be kind of a wide range of Hamiltonian-like operators. These aren't necessarily like specific things. They're, I think the only requirement is that they have to somehow describe a transition from one state to another. So like creation and annihilation operators, if you think of that kind of a thing, that's sort of what those have to be. And this is just like, basically, if you write out these commutators, this is just another way to write it without any of that in there. And let's see, the nice, yeah, I don't know, I can't remember what all the points were that I had about this one. But essentially, this one ensures that your reduced density matrix always stays positive, just like by construction of like how he got to this stuff. It's like very like mathematically rigorous way of doing it. The kind of the issue is that as you go towards like, you know, infinite time, you will achieve the thermal state with your density matrix, but you will not preserve translational symmetry, which is a problem. But you can include additional terms to correct that. But then the issue is that you no longer achieve the thermal state as time goes to infinity. So it's sort of a trade-off of like, which would you rather have? And then there's the Nakajima-Zwanzig master equation, where the idea behind this one is to essentially use projector operators to just get down to like the part of the density matrix that you want. And these are both just different representations. The superscript I just essentially means that you're writing it in the interaction picture. And the nice thing about this one is that it's actually formally exact. Like this is an infinite order perturbation theory is how you get to this, where this guy is like a time ordering operator. The problem with this one is that usually for any sort of practical system, you can't solve this. So yeah. And that's pretty much it.
Oh,
Here's my presentation. My name is Adam Flesche. I'm enrolled in quantum chemistry in spring 2023. I'm talking about dissipation in the context of this master equation. Our master equation, like this one, it has two main parts. It has the first part, we've probably all seen it by now. It was included in a few presentations for myself, but that's the part that describes coherent evolution. The second part is just the dissipative effects on the system. This L term, Lindblad operates, and that's going to take this form right here. These AA dagger operators, basically what those are just going to be telling us is how our system is relaxing. Our gamma that I have up here is the dissipation constant, or at least it should be constant. It is. But our density matrix will remain Hermitian regardless of our selection for gamma or A, which is pretty nice. We can still work with that now. And how do we apply this? We'll consider a two-level system first. So instead of AA dagger, I'm just going to be referring to a grounded excited state. The only two levels in this system. We should be able to determine this excited state probability is this. It simplifies to this term right here.
So how do you go from equation 2 to equation 3?
So this first part here, it will commute to 0. There are a few parts. I think this first part here as well gets neglected. We just sort of left these two terms.
So you take your top equation and find matrix evidence by applying ket and bra and ket from left and right to each term.
Yes.
Okay.
It's just a matrix algebra, I guess. The decoherence of coherence can be expressed with this. It utilizes our gamma, which is our dissipation coefficient.
So for populations, you apply bra and ket with coinciding indices.
Right.
Yeah. And for decoherence, you apply bra and ket with different indices.
Yeah.
Okay.
Yeah, that's just going to be the rate of decay. Gamma, I guess, in the case of spontaneous emission, that small term over here. It's not that important how we get that right now, but
Quickest possible summary of last 3 lectures in our class.
In the case of a damped harmonic oscillator, we're going to be doing some similar things. We're going to use end states, but we want to still try and focus on 2 of them. We're going to do similar algebra to find the probability of system having n photons. So the photon count can sort of represent a state index. That will simplify to this term over here. Sorry, the mouth is kind of covering it. But that being said, this AA dagger term, as I've sort of shown up here, I'm using AA dagger, of course, to represent these states. And so A dagger A represent the expectation value of photon count for the system. And here's how you apply time evolution to it. It's going to be in the exponential.
As for the spin-boson problems, what the spin-boson model is a two-state system. So it's a system such that we have a continuous degree of freedom. In this case, this paper used the term Q for that. And then it's creating a different potential. And what we see is we see this double minima in the potential. And what you are doing is you have slightly different degrees of omega between the excited and the ground state in these two wells, which is denoted by this epsilon here. And what we see is that if it's isolated from the environment, we get this Hamiltonian here, where this portion of the Hamiltonian is describing the tunneling between the two wells. And this is talking about how they interact within the well. So the one thing to note here, they are using these sigma x and z, which are the Pauli matrices, and they have chose a basis so that the sigma z, the eigenstate of sigma z, will be +1 if the system is localized in this well, and -1 if it's localized in this well. But in most realistic systems, we're going to have interaction with environment, and this interaction can be significant enough to change not only the quantitative but qualitative behaviors. And this is due to a term that takes this form where the sigma z is, again, the Pauli matrix, and the omega is some operator representing the environment. So what you actually get for when it's interacting with the environment is you get this form, and this is what is termed the spin-boson Hamiltonian, which I have color-coded to represent different sections of the Hamiltonian. So this pink color is the system Hamiltonian, which you notice is the same as the previous. This orange color is the Hamiltonian of the bath, and then this blue is the interaction Hamiltonian. So again, we note that we have this tunneling factor, and here we have a factor that's talking about dealing with the distance between here. That's what this Q is this distance. The C, and I guess it just appears here. I thought it appeared one other place. The C is the coupling between the system and the oscillator. And so that's what we get for this. And then if I understand this correctly, we have the spectral function, which can describe the coupling between the system and the oscillators and its dependence. And it depends on the frequency and how the frequency relates to the tunneling factor. So if we get a cutoff frequency that's significantly less than the tunneling factor, it has a power law behavior, which we can see in this equation. And then what they note is that the behavior changes significantly depending on what this value of S is. And without looking at the notes I have on the slide, I don't remember how it changes. But it has a different effect for S greater than 1 than S between 0 and 1. And S equals 1 is the case that is what they called an important case, because it's the point between these two. That's
Okay.
Hi everyone. I'll be giving a presentation on Tavis-Cummings Hamiltonian, which helps to solve this problem of an N interaction between an N molecule with a single mode radiation. So during my last presentation, I talked about the Tavis-Cummings Hamiltonians, which involves the interaction of one two-level system with a single mode radiation, and James Cummings was able to come up with a solution to the problem. So what Tavis did was to what Tavis is trying to do is to solve the problem caused by the interaction of N two-level system with a single mode quantized radiation. And why he's trying to do that is because most of our real-life models are involved with not just one two-level system, but more than N two-level systems, such as the laser. So here he assumed that the system here the model is done in resonance, so there was no radiation loss due to interaction. And because of that, because of this ideal or perfect model, he was able to generate the solution, the exact solutions for the interaction of the Hamiltonian. And based on his research, what he did was to compare the solution, the exact solutions for the problem with certain approximations also done by people, such as the average field approach and the modified two-level model approach. But based on this presentation, I will just be dealing on how he was able to formulate the problem and also solve the exact solution. Okay. So for him to develop this Hamiltonian, he used 3 methods to develop this Hamiltonian. First of all, he started with the general Hamiltonian, which we all know, or we passionately know as a semi-classical Hamiltonian. He was able to generate the semi-classical Hamiltonian, or the quantized Hamiltonian that was described by James Cummings Hamiltonian, and he further simplified it using and this is the general semi-classical or quantized Hamiltonian generated by James Cummings. And from this,
can you start from the beginning of your slide? You have 3 terms there. Can you just call what these notations means? HM, HF, HI.
Okay. So HM means the Hamiltonian of the molecule, HF the field, and HI the interaction. And this is the popular Hamiltonian, which this follows the potential energy plus the kinetic energy. And for our interaction, this was something we explained when we're talking about the light matter interactions. Where
A in this expression.
Yes.
A vector there. How you call it?
Vector potential. Vector potential.
Okay. The vector potential of the field, right?
Yes, vector potential of the field, yes. So why this Hamiltonian is for the electric field, why he here is the electric field and H here for some reason was the magnetic field. I don't know why H was used, but I just went with it.
And C is speed of light or the distance?
Yes, speed of light.
Why not distance? C squared.
Yes, it's the speed of light.
I think this distance is squared.
No, it's just a square.
You wish to t squared or something distance is squared. Square of distance.
Like it should be not just 2mc squared, it should be some other term in the denominator.
I think it should be a square of the distance.
No. Dinesh is expecting to see dipole approximation, or distance between positive and negative charge is multiplied by electric field. And if you see, Patricia is showing it as an approximation, as a last line of this equation. But more general, doesn't have distance, it has only momentum and vector potential. Thank you for the question.
Okay, so this is the interaction for, this is when one two-level system interacts with a single mode radiation. So what if we have the interactions that involve multiple two-level systems interacting with a single mode vibration radiations? This is what we have here. And after a series of gate transformations and dipole approximations that was not mentioned in the slides, they were able to arrive this equation. This equation looks similar to what James Cummings and Hamiltonian gave us, except for the summations, where here is the electric field and here is the dipole moment. So if further simplified this, term using the molecular and feed quantization, my bad, there were really a lot of calculations involved on how he was able to simplify from the previous equation to what we have here, which was not mentioned here. But after simplifications by different approximation, he was able to arrive at these Hamiltonians of the system, which involves this first two term is our unperturbed Hamiltonian, and this relates to our perturbed Hamiltonian, as stated here. So the eigenstates of the non-interactive system. So to formulate our problems, we first need to get the eigenstates of the non-interactive system. So the eigenstates of the non-interactive system was defined in this, where the eigenstates of this was this, for the unperturbed. And for this HAR3 is a bit confusing, but if you can imagine it as when we're doing our angular momentum, where we describe.
What is your R again?
Yes, that's what I'm trying to explain. Like our angular momentum, this HAR3, when we're describing in the first session of the class, when we're describing angular momentum, where we have Lx, Ly, Lz. So the HAR3 here represents like Lz. So it was just given as R3. Like R1, R2, R3. I think that was how Tavis explained his momentum is HAR3. So HAR3 can be similar to what we have as Lz. So
R is just the angular momentum of the system.
Please explain it by words.
Yes.
So
just coordinates.
Yes, the coordinates, yes. And
what is plus and minus then?
yes, the raising and lowering operator of the.
Okay. So it's laser apparatus based on the angular momentum.
Yes, this.
So let me help so that we progress quicker forward. System of n two-level systems, which are speed 1/2. One assumes that there is an addition of angular momentum of n speed 1/2 system, and then one gets is a overall system with n capital over 2 angular momentum. And for this combined system, one practices the projections of angular momentum and raising and lowering operators. So it is a basis to progress further.
Okay, thank you. So this is what I explained, that this state here are formally identical to the states that we have for the total angular momentum and the total z component of momentum for a system of spin. And the RM states are formed in the same way from single molecule states, spin up, spin down. So something I forgot to mention, because of commutation relationship, it was noticed that this Hamiltonian, this total Hamiltonian commutes with HO, H0 and R3 commutes with both them. So we can say that they both have the same eigenstates. So, and because of that, we're able to get something like this. So to be able to construct this problem, we have to turn this state into a matrix where your dimensions are 2 raised to power n, where n is your number of two-level systems in the model. So what we have here, this is a representation of a matrix where we have the diagonal that are non-zero elements. The diagonals are also splitted into smaller boxes, where they assist to.
We will get only diagonal elements in this Hamiltonian.
Yes.
You just
Block diagonal.
block diagonals. Okay, so it means like what you mark is not a single element. It's a, I don't know, 2 by 2, 3 by 3 kind of small pieces.
Yes. Yes. So these elements. Yes. I think I do not get your question. Yes. I do not get your questions.
No,
There's no question.
Oh, okay.
It means you already answered.
What do you call books? We can call it book.
Oh, okay. Yes. Okay. So, and previously I said this for this 2 by 2 block matrix, we have some the diagonal elements are also splitted into smaller smaller blocks of matrices also, in which can be calculated using this formula, and them having the dimensions of 2r plus 1. Sorry, this is error. So assuming that we have the states rc j as the eigenstate of h squared r3. Recalling we already have our in the previous slide our eigenstate to be this. So we are assuming that if you assume that our r cube our state is this. So this is also m, but your m is c minus n. So we are making the summation, our states, the summation of all the states here for an n two-level systems. So there was a lot of math problems being solved that went from here to here, which I tried to understand how they were able to use some basic approximations and boundary conditions to define what went from here, how to define this and this. But from what Travis explained, it was able to confirm this problem and get your eigen problems to be this. Why your an, sorry, this is an, is from here. So it's acceptable to define your eigenvectors as this. Why your q is your eigenvalue. So the largest value of q for a given value of r and c corresponds to the ground state of the system, and for the ground state of the system.
What is your identical block equation? What was your identical block equation?
This?
Yeah, you said.
Yes, this represents this.
No.
That's what this is for me.
Yes.
For
Why you have kind of this? Why your system returns to this kind of block-like Hamiltonian? Yes. What's the physical reason for this? Why it's not having everything spread with some coefficients?
Because they wanted to, it was trying to use a matrix to solve the eigenvector.
This would be easy to solve.
Yes,
you can really solve it block by block.
Yes.
But what's the physical reason results on making your Hamiltonian like this?
Because you can easily diagonalize the matrix to give you the eigenvectors and eigenvalue.
Okay, so can you repeat again? What is this n? What's the difference between n, m, r prime?
Yes, it's just different notations for your different notation, basis of different eigenstates. Is that what you're asking? Yes.
But what is the index m and r stays for?
I just assumed this.
Yeah, but just give them a name with human words.
States?
No,
Wave
no,
function?
Like total speed, z projection of spin.
Okay, is that all?
So let's go back to Hamiltonian. Yes. So R is total spin, M is magnetic projection, and
oh yes, of
N
course.
is number of quanta in the field.
Yes. Yes. Okay. Yes, of course. Total spin, like the way we have in our angular momentum, total spin, then magnetic projections, and number of quanta.
And it looks like, because you have these block elements, right? In other words, your quantum state of the field is coupled with some specific states. Most of the states are not coupled with electric fields. That's why you have zeros in a non-diagonal. Most of the non-diagonal elements are zeros, because your field is not really coupled with everything.
Yes.
It couples with some specific elements with these specific angular momentums and specific spin position, spin number, right?
In brief, answer to your question is energy conservation.
Oh, okay.
So total number of quanta in the system doesn't change because it is isolated.
Isolated, yes.
If electronic system in ground and photon is state number n, it can exchange only one photon and distribute over this and that states.
Okay. Yes. Yes. Okay.
And in between the only nearest.
Yes.
Yeah. In sense of
states with the nearest angular momentum.
Okay. Yes, because this model was Travis make sure that this model was done in resonance. There was no radiation loss in this model. So, to solve this problem, it started with this. To solve this problem, recursion. Yes, to solve this recursion problem can be solved starting from this. I tried to see how it did it to be able to get the values for your AN, or realistically, I still don't. But I know it was able to arrive with AN to be this. The eigenvectors was solved to be this. And
what is tandem?
What is what?
Tandem.
So, oh, sorry, understand. Sorry.
Tandem is different.
Sorry, it's just, this is just me. Sorry, if it's wrong, I think it's just me. I don't.
Probably meant to say that.
Okay. No.
It should be for them.
No. Understand. That was what I was trying to say. Understand, like. Okay, sorry. So the eigenvectors was solved as this, and we can use, if you recall this, in these wave functions that was brought up initially, where we have a plus the plus our wave functions, we can be able to impute this here and get our value for our eigenvectors. So if you visualize the graphical illustrations of the solution, as I said earlier, that AN shows AN as a function of n for several values of R, C, and J. So if J equals to 0, it means that we have our ground state, and you see this shows that our J is in a ground state, and if J equals to 1 is our excited state, and J equals to 2R is the most highly excited state. This is a graphical illustration. So Dr. Killing asked me a question that
this is not in a printed version.
Yes, sorry. Sorry, he asked me a question that what if that my two-level system, my n equals to 2 for my two-level system, how am I able to solve it? So I tried to look at it and say, okay, what approach am I going to use? So from my very limited knowledge, I decided to start from the matrix block, since that we have the dimensions to be 2 raised to power n, and the 2 and our n means how many molecules of two-level systems we have. And I said, oh, since our dimension is 2, our n equals to 2. So for that means our dimensions are 4, and we can be able to solve for the elements in the diagonals using this formula that I explained earlier. And from that, we are able to assume that they were just two blocks in diagonal based on the formula, assuming R equals to n over 2. So the Hamiltonian of the molecule interacting with a single mode using the molecular quantization. I use the molecular quantization explained by Travis to say the summation of from J equals to 1 equals to 2. And I came up with this, and this is the dipole moment for the system electric field. And if I have like the units for this, I think I should be able to solve for the Hamiltonian of the interaction, and I could be able to get the eigenvalues of the system by knowing the coupling strength, which is your K. Your C mostly is the same as your R, and your lambda, which is your eigenvalue. So if we know the coupling strength, to be able to find the value of C. So, and the eigenvectors can also be solved using the formula I showed previously here.
You are writing this for 2 helium-like atom, right?
Yes, two level system. So this is I don't know if this is correct, but I just did a lot of. Okay, thank you.
Okay, let's think.
What I will be talking about, very bright light, is doing solutions with a source and the Spin-Boson model. So we will start with solutions with a source. So what we what we are starting with, so we have a schematic here for like a laser. So you've got your ground state, and then you've got your states where you actually do the lasing. And all these gammas and these R's are either decay or excitation rates, depending on which way they're going. So all the gammas are decay, the R is an excitation. So what the solution with the source, is doing is we're using a continuous excitation on the model to calculate dynamics. And what it's actually doing is it's resulting in a superposition of the evolution operator being applied to the initial conditions. And yeah. And then off to the side, we have the equation of motions for the population matrix here. So the major thing we note is that we can solve it into the integratable form. And
all right, so I'll be presenting on the semi-classical laser theory that was derived by Willis Lamb, more famous for the Lamb splitting. And so it's noted right here in red, contributed to the early development of the laser. And so in 1954, the first functional maser microwave amplification stimulated emission of radiation was constructed, though at that time there wasn't really a formal mathematical explanation behind how they really worked. Shortly after collecting his Nobel Prize for Lamb splitting, he set to work on deriving the basis of lasers. And some brief history of lasers. Sorry. So it's light amplification by stimulated emission of radiation. What does that exactly mean? It's not a Z, it's an S. So we have a set of atoms that are interacting with an electromagnetic field inside of some cavity, which I know we've already seen. The cavity is sized such that it supports a single set of eigenfrequencies. The excited state of the atoms are resonant with at least one of those eigenfrequencies. And so when they try and release their energy to fall back to a relaxed ground state, the only way they can do that is by transferring that energy into the external electric field. So the emission part occurs when the excited state is sufficiently populated, i.e. we have a population inversion, and the state 2 is more heavily populated than state 1, the ground state. And so just to sort of elaborate on that, what does that exactly mean? Are they like sort of like some sort of light bulb? And the answer is no, they actually work on an entirely different set of math compared to like normal light bulbs or LEDs. So rather than just being a focused beam of light, they are single wavelength, as I said, 550 nanometers right here on this little one I'm holding. Single wavelength beams of light that arise from the fact that only certain frequencies can be sort of stably emitted out of our specifically sized category or cavity. So it's sort of, with gas lasers at least, the closest example would be sort of like I guess it'd be like those like resonant tubes that like people play with in physics labs. You put a cap on one and it changes the frequency. Sized for gas atoms. They can only emit specific frequencies that are resonant with the usually noble gas constants inside of them. So they're like a really fancy neon light. Oop, too far. So what was Lamb's model? So Lamb's model for a laser, taking the simplest and easiest to calculate example, has a ring-based cavity with a linearly polarized electric field. So inside of that, when you have that setup, the only appreciable frequencies that you can get follow the equation Vm over m pi c over s is equal to kmc. S being the circumference of the ring cavity, km being the corresponding wave number, and m is just a nice integer on the order of 10 to the 6th, so a million, to make it work nice. Because otherwise, and obviously c is like the speed of light, it's constant. I was writing notes to myself on my copy. So we have our two equations here that I'm not going to go before because I didn't have access to that. But there are our equations for frequency and velocity. So now if we plug our population data equation into that, we can get these two bottom equations.
For polarization, right?
Yes. What more do you want to?
Can you explain what all the calligraphic signal
Ah.
symbols are?
I was
Yes, like beautiful logo, or what is it like? Yeah. This one, right?
Like there's like looks like a calligraphic P, a calligraphic
P.
E or G, another calligraphic P.
Yeah, there's a
big capital.
yeah, there's a calligraphic L, a calligraphic sigma, a calligraphic rho or P.
What they mean? We didn't ask you to call the letters. We're asking what do they mean?
So the calligraphic P is the polarization. And the
Kind of B and epsilon.
I think it's supposed to be an L, a calligraphic L.
Oh, okay.
It's a C.
Yeah.
I read the entire notes on this thinking it was an L. Yeah. Ah, yeah. So it's the loss. Oh, that would. See, now I was wondering why I couldn't figure out where they were putting loss into this and thinking that was a C, but if it's an L, then of course it's loss.
Writing in Dimitri?
Dimitri is writing.
I saw you talking and writing simultaneously.
Let's on the fly ask Adam just based on this equation.
Does it look familiar?
Who needs damped cavity? Okay, like lasers.
Yes, there will be some more familiar ones coming up. But yeah, so the L is our energy loss to the cavity walls, since we have a gas inside of a real gas inside of a container. It has collisions. And this, I thought it was a sigma. It is a sigma, right?
Oh, no, it's calligraphic E for E vector, E electric field strength.
Yes. Yes, it's the strength of our electric field. And then, of course, if you really want to go in depth, you can continue on to calculate losses that are caused by imperfections in the mirrors of your cavity, but that's much.
Also,
Then what's the other?
little p or little rho, I don't know what is it, like in the next set of equations. Wait, big calligraphic p,
Right,
yeah,
where your
this
laser
one.
is.
This one?
Yeah, and then the next row in the equation, what are they?
So these rows are your population.
And indexes stays for state A, state B, or what is it?
Yes.
But then why is there are two indexes if it's just the population of a state? Why is it two indexes? Why is it A, B, B? What does it mean?
It's a two-state system, isn't it?
But you cannot populate both. Okay.
Why it is row A instead of row A? Why one uses two indices?
Looks like it's a matrix element rather than just the value, right? Rather than just population is just a number, right?
It's like speech defect instead of row A, row A.
You know, it's for sure population.
Yes. And it
It's not just a speech defect.
what I'm thinking it is that, as I said, it is for sure population, but it's the like total resting ground population and the total excited population, right? Because the laser doesn't exist as a laser beam until we have a population inversion where the number of excited states is greater than the number of ground states.
Yep.
So T stays for the ground state, A stays for the excited state. Indexes. Yes, yes, okay. And then this calligraphic little rho or little p squared.
Yes.
In front of the electric field strength. Transition.
Dipole.
Why?
Thank you, Dimitri.
But did we say that the big letters was polarization, right?
Yes.
And little one is a transition dipole or backward.
No,
Okay.
that's fine.
Ah, okay, good. Okay.
You need a magnetic field for a laser to work as well. It's a great number of components.
So the only things which is left at the very last formula, last two formulas, gamma and omega. Well, I guess omega and nu. What's the difference between omega and nu? I guess both. I was thinking it should be frequency.
I was understanding omega as frequency as well, but where are you?
Frequency of the transition, AB transition, right?
Yes.
And then nu,
New. Curvy.
nu, omega minus nu. At the very bottom.
Yeah, like omega minus two.
Oh, this?
Yeah. Or V, I don't know. You
It looks like a nude, but yeah.
Oh,
what's the meaning of this one?
I was reading it as V. That should be
But Dimitri, you already kind of give you the hint.
yeah. Velocity.
Oh,
They're both frequencies. At least I'm assuming that they're both
well,
frequencies.
technically, again, what is a laser? You kind of give it as idea. So you should have a crystal. Well, if you talk about solid laser, there is a crystal, and crystal has some impurities, right?
Mhm.
So impurities are very important, and because impurities will contribute to this
Higher energy.
state, I guess, which is called A here, because they have long-living states where you can create this reverse population. I mean, kind of a lot of population comparing to the, but you cannot, when you kind of in this material, right? You also have host states. So I guess blue one, nu with blue level corresponds to the energy of the host material, of the host crystal.
Like,
Right.
Like U is the frequency of the
resonator.
Yeah,
I
that's
remember Stephen was introducing the C numbers. So it's like when U is for resonator and omega is for the active medium.
Okay.
Okay, then what's lambda? Or not lambda?
Gamma. The last one, gamma.
Don't want to take off your brain. I think Adam, you explained what gamma was, but I can't remember what you said it was. Because
On the keyboard. Escape on the keyboard.
I know me and Tori were both trying to find out what gamma is, and it's
Let's ask Adam.
Are you sure it's the same gamma here?
But what was your gamma?
Yeah, that gamma was the dissipation rate, it was a dissipation
Was
constant.
damping, right?
Yeah.
Should we have damping here?
Since both theories were borrowed from the same textbook, there is a chance that Westra was continuously using letter gamma for that.
So it's damping.
Sorry.
Each has.
Huh?
Frequency is a word on.
No, omega frequency, gamma damping. Patricia?
Yeah, I think about that, damping. For its introduction, about that, you were in resonance. Then in resonance, how is damping apart?
Intuitive resonance doesn't exist. It's
We always have some damping in the system, right? Stephen was mentioning something like not perfect mirrors, right? Or any kind of imperfection.
Good.
Will result on the damping.
as I sort of just like casually explained. If we are thinking about our laser chamber that we're talking about in this example as a physical object, doesn't want to come off. We have a ring that, as I said, it's a neon light ring of a very specific size. And the way that it actually forms the laser beam rather than just glowing quite prettily is that by having it of a specific size, it's only capable of really sustaining frequencies around it of a very specific type, like one or two singular like frequencies.
So the light is traveling around the ring?
It's mirrored.
Or is it like you've got like an inner mirror and an outer mirror and it's just like circular shaped? I don't know.
I wouldn't draw the circle shape on the ring resonator. Sometimes people assume 4 mirrors and it travels in rectangular rather than.
Okay, so the idea is to make the light move
Around, yes.
Yeah, okay.
It's like a particle collider, but we're not working with particles, we're working with beams of light. Does that sort of make sense? Because this whole thing is inside an electromagnetic field.
Okay, sorry, just to clarify. So what you're saying is that despite the fact that you said they were in resonance, you still have to like
Account for the fact that it's a real object, and so it has imperfect states and it's losing energy along the way. So Dimitri actually made a change to one of the later slides to account for that. I don't believe we're done with this slide. Oh, I should have put that on. So we now have, just moving on, we have this equation for our population and the various components of it. We plug that into our previous two equations, where in this case, what I was going to mention, V, this capital V here, is the volume of our cavity. And now you ask, Stephen, we have all of these script letters again that you haven't introduced. What are those? They're this. The script A and script B. Script A is the, oh yeah, I put it on there because I knew I would want, is the linear gain parameter, and script B is the saturation parameter. Yes.
Are those related to the Einstein coefficients?
Remind me about the Einstein coefficients.
So like the A and B coefficients describe the like the rate of, I think, absorption and stimulated emission respectively, or no, B is both types of emission. I think it's that way around.
A is spontaneous, B depending on which you're looking at is either absorption or stimulated emission.
Yeah.
So what is advocated for Steve? It's healthier not to make it parallel because the meaning is inverse and not linear. So what is used as A is stimulated absorption. And B is something very different. So let us say, therefore they use calligraphic to be different.
Because remember, we're pumping energy into this constantly to add it. It's like I said, it's like a neon light. It doesn't just glow by itself. It needs energy added.
Calligraphic A is like an Einstein coefficient B. And this little gamma is somewhat related to Einstein coefficient A, which is like, is not for mental sanity, but it's better not to make these parallels.
Okay.
What is and not in the calligraphic A equation.
And not this one is the same one as our population.
Okay.
So it's N naught over
Initial population.
And now there is a question, what is lambda A and lambda B?
Also gamma A and gamma B.
Yes,
Before we just have gamma.
so gamma is damping and lambda is pumping. Because in addition to these two levels, there are many other levels that are excited by regular like Flesche lamp. And there is a pumping rate for our active levels.
just because one energy level is stable doesn't mean that others don't exist.
So is N not like how many more excited atoms you have than relaxed, essentially?
I think
In a way, yes.
RS showing you, RS showing how much of them were lost, right?
Population in steady state solution for population inversion.
Okay.
Yes.
But is it true? And not is it initial population?
No, steady state.
Steady state, yes.
Should move some of this around. And so now simplifying those, sorry, we now have these two equations, which we can now plug in all of that into as well. And then skipping over the simplification because it's just a lot of crossing out terms.
But the calligraphic E, the electric field amplitude squared, is proportional to the number of quanta. Then one can convert these equations into in terms of number of quanta into the mode of the field. That taught us how to do.
But what exactly is the goal through these equations? What is our main goal to get at the end? What are the characteristics of lasers?
The end goal is that with these final two equations, we can now actually determine the behavior of the laser, in that we can determine the we should be able to determine the threshold energy, which is the minimum energy we need to sort of reach inside of our cavity chamber for it to actually laze.
Looks like you don't have energy in this equation.
Number of quanta in the mode.
Oh, and little n is number of quanta.
Yes, multiplied by h bar omega will be energy.
Okay.
I knew I should have kept that equation. I cut it because it didn't feel like it fit. But yes, it is possible to determine sort of the exact number of photons we have in our laser beam through what we have here. And it's actually quite a simple equation.
But then we need kind of the high energies are better. What? The high energy is generated in the initial moment of time. I mean, because it also depends on time. I'm just trying to understand how this characterizes a laser. In other words, characterize means good laser versus bad laser. What is better? Big N, big number, like when it's a big number of photons can be photon modes, photons, number of photons, right, are generated in the resonator. Is it? In a short period of time, of course, right?
Yes, I believe that should give you a brighter and more powerful laser, since you'll be able to transmit.
What we contribute, and maybe Max will share his own vision on this answer on this question. We will re-ask this question when you presenting.
You can start your presentation with this answer.
So one can measure amount of energy pumped into the laser system, and one can measure energy going out of the laser system, and then one can make a ratio: energy out divided by energy in. If this ratio will be linear if it is a regular photodiode, but if suddenly it changes its curvature and provides much bigger gain, changing this curvature of gain versus input, it is a criterion of laser generation. And Steven is making his effort to explain how one can get this abrupt raise of the energy coming out.
So far in your previous slide, the graph which you were showing in the previous slide based on this solution of equation, previous slide. Yeah, so it's given us only output photons, right?
Yes.
Without including how much it was inserted, how much energy or how much photons it was inserted to the laser material.
Yes.
Mm-hmm.
So this, I believe, would be comparing sort of it's the same graph, but now we have our A minus our C. And I mentioned a very specific term called the laser threshold, which you'll be able to see referenced on the slide below this. The laser threshold is a critical term because it's actually, as I said, the amount of energy that you need to reach before your laser will begin to laser. Before that, it's just a box filled with light. Once you reach the laser threshold, which is, as Dimitri wrote, well, A is equal to C. Formally, if you had a perfect sort of laser system with no inefficiencies, perfect mirrors, no losses anywhere, it'd be A is equal to script B. C is taking into account losses due to an imperfect system. And so we can see the higher our A minus C, the more number of quanta we're getting out and a better laser beam. And then Dimitri mentioned a critical phrase, nonlinear. So the reason why this threshold is considered so important is not only, as I said, it determines when it becomes a laser, it's because we can define it by putting energy in until we reach the point where our A is equal to our losses and emission. And then after that, the amount of photons in our laser grows quite rapidly. So we have a nonlinear production, hence the threshold condition. It's the lowest amount of excitation at which the emission by the laser is dominated by stimulated emission from the field and relaxations rather than spontaneous emissions, just a light bulb. And now what I was asked to include to help lead into Max's talk. The laser threshold as a second order phase transition. So in this case, with our perfect system, A is equal to B. And this is also why I prompted about P representation. So in a condition where we are far, yeah, I thought I had more. But our expectation value for our energy, we can represent with this equation right here. In cases where it's far below the threshold value.
Is it energy or field? I'm not sure. I'm just asking.
It might have been expectation value of the energy of the electric field.
Okay, please go ahead.
But the key takeaway is what we have here at the bottom, is that our expectation value, if we have sigma minus sigma t is below 0, it's below the threshold, our expectation value of our emission is 0. If it's above the threshold, then it's A over B times this geometric series.
So there's a function with discontinuity.
Yes.
Okay. And this was for the laser.
C defines the threshold, right? The coefficient C.
C defines our
defines the loss of energy.
C is the loss, A is pumping.
No, before it was B.
there's two.
Several slides ago, the calligraphic A and calligraphic B.
Yes. So which slide do we want? This one. Yes. The calligraphic B is our loss.
Was a loss, right?
Yes. For an ideal system.
Yeah, but then you kind of introduce the case C equals A. It's some kind of regime which allows you exactly the threshold when nothing is growing. Threshold means it's reaching its plateau, right?
Yes, it is. So when A is equal to C, that is when stimulated emission is now the dominant factor and it's outpacing spontaneous emission. It is now an actual laser.
Well, exactly. And this, they're kind of equivalent to each other. But
yes, you need to cross this point for it to become a laser. Before that, it's just taking in light or taking in
It's
energy.
a property of your instrument, and A is something you can tweak to turn the knob.
So
no, I thought it's backward, but it's in this.
You can control losses. It's property of material.
But it is not losses.
A is energy in.
Which you
So-
can control.
Yes.
Yeah.
And B is our losses for an ideal system.
They call it saturation.
Well, it doesn't matter how we call, we understand what is it.
But yes, A is what we're putting in, B is what we're getting out. We need to have what we're putting in be at least equal to what we are getting out.
Say equals B means you're in the.
Your energy is equal to the amount of energy that's coming out, which is the threshold you have to cross for it to
Then
be in.
in this case, you will have no any light, right?
Yes, that's why it's the point you have to cross.
Okay, good. So we are in this range when nothing is coming out.
Yes. As long as A is larger than B, then you have nothing coming out. It's not a laser. Once B becomes larger than A, then you have a laser. It's defined that the point when it becomes a laser is when B is equal to A. What we have here with this red C is accounting for non-ideal system losses as well. B only accounts for ideal mathematical losses of our energy. C accounts for the losses to our instrument.
Okay, so in other words, this can be really measured.
Yes.
Okay, you can estimate it from measurements.
I have no idea.
Likely, this A equals B is needed only to solve for this nonlinear equation. Right?
But again, it's an average E. You said it's not energy.
I would bet for electric field.
Strength.
Yes. And then square. Then the electric field square will be energy, and it will be linear as offset between one and down.
as soon as you reach in your threshold and getting higher than threshold, then electric field will be, what you said, proportional to what?
It's proportional.
And again, this little gamma,
This little sigma here is
sigma, sorry.
so our energy in is alpha times sigma.
Yeah, I guess they're proportional to your calligraphic NB, but
Yes,
but
yes.
then sigma means
Sigma is the population inversion.
inversion population.
Yeah.
But they
Thank
have sigma and sigma t.
Sigma t is the changes we need to a population inversion to get our losses. Our
Yes,
L.
for threshold.
Uh-huh.
Yeah.
Okay. So just kind of a different way to
A way to write it simply.
reformulate this A, B kind of letters through connecting them to the something which you can measure, because your average electric field probably can be measured through observables.
It's after it's an electromagnetic field, which is the next point that I was asking. Lasers as magnets. So, and I say, Stephen, what are you talking about? A laser is not a magnet. A magnet is a magnetic field and a laser is a beam of light. Well,
Asking you this question.
I suppose you are. But
Hypothetically, we all are.
yes.
Oh, you just assuming this was a question.
Well, obviously, as you all laughed when I said lasers as magnets. But so the typical treatment of laser behavior is a self-consistent field where we have some expectation value of our field strength, and from that we're deriving the strength of our beam of light, and as a second order phase transition. Well, and to that you say, now hold on, that sounds very similar to how we would describe the behavior of a magnet with a second order transition of a consistent field of some electromagnetic strength. With our expectation value of our magnetic field being n, it's mu, or no, that's mu, yeah, mu. Mu tan h, mu h over the Boltzmann constant times t. And now for a three-dimensional case, this actually has not been solved yet. But it can be approximated by taking that h and replacing it with h plus lambda m, which is just an approximated constant to account for the interacting field strength. And we get this equation, which should look familiar, or will very shortly. And we also get this very familiar looking equation down here, where we now have A over B Tc for the critical temperature, or the Curie temperature, minus T over T 1/2. And our expectation value below that, so, is 0, and above that is that.
Should you define what is your TC once again? I mean, not just name it, but define it.
Tc is the Curie temperature. It is the critical point that above which a permanent magnet loses its magnetism. It's really quite spectacular if you watch a demo of it.
Spins just becomes.
Spins now have the energy, yes, they now have the energy that they are no longer locked into a magnetic field. They can now spin freely again. And so we lose our magnetics.
Completely beyond the things you're talking about, but I'm just curious. I really don't remember. People say critical temperature and Curie temperature. Is it the same or not the same?
They are the same.
Ah, okay, just different way how you call them. Oh, just for the phase transition kind.
Yes.
So then could you hypothetically make a laser just with
With
magnets?
magnets.
You have a strong enough.
So the only problem, I think, again, here is a trick, same as was a question of Patricia to Adam, right? What's the difference between vibrational damping versus electronic damping? So mathematical formula is the same, but physical meaning, I mean, like the observables, of course, are different, right? Different energies, different kind of properties. Pretty much the same here. So mathematical formula is the same, but there is no light coming out of the magnet, right? But there is orientation, a kind of coherency in the spin behavior.
And you need a magnet to make a laser.
Well, there's a difference. There are similarities and differences. If one plots this figure, then it will be non-zero at low temperatures. Would you please flip back? here, if you notice these conditions, if one has this sigma parameter, sigma threshold, it goes when sigma grows bigger. So,
Yeah, the reverse behavior is the same.
right, it has non-zero behavior at different sides of the threshold. But in both cases, it is discontinuous function with infinite derivative, which is a signature of a phase transition. The coherent.
And that actually is the end.
Okay, let's see.
Okay, so I'm going to be introducing more topics about laser theory, focusing on fixed atomic population and a quantum model. So first,
I have immediately the question. So it looks like before it was also laser theory.
Yes, mine was classical, his is quantum.
yeah. So quickly, just to briefly overview why we want to model lasers is so we can increase their efficiency, so we can maximize the population inversions, get different wavelengths, maximize the brightness, and minimize how much energy we have to input. And so whenever we want to apply these models to real situations, we have to have spectroscopic measurements for whatever our active medium is, so we can know their, so lasers will work. There we go. Okay, so we can know their energy levels and the lifetime of the states, so we can model the rates. And then we need to have a model of our pumping method. So usually it's either electrical or optical. The basics, we've already talked about pumping, so I won't get into that, but we also have an active medium, and that's just whatever our atoms or molecules are that we're exciting. So we place these into a cavity, which I think I missed the part where Stephen was talking about what the cavity is there. It's just so we can contain all the light, so we can only direct it out into one direction. So I do want to make a correction to this. Ignore the second line. I was thinking about this while the presentations were going, but so increasing the intensity of pumping will create a faster population inversion, but also based on the idea of detailed balance, having a higher rate will also increase the overall population of our excited states. And then finally, we have simulated emission. So going back to detailed balance, the whole idea of detailed balance is that the population and equilibriums are based on the rate of absorption and emissions. So from that, we can establish this equation where we have the excited state rate of change is equal to the inverse of the, or the negative of the ground state change. And so we can adapt this to a multi-level model with n energy levels. So it's not just a two-state system. And we have this function where P is the probability of a state n's occupancy. So n is just a quantum number corresponding to our states. And then P, since it's the probability, we can also liken it to the density matrix operator.
And get N2 and N1, not both. What is N2 and N1?
Oh yeah, I was going to talk about that here. So N2 and N1. N1 is the ground state, just ground state population. N2 is any excited state population. So it can be the first excited state or higher. And so when we generalize it, N2 will represent all of the excited electrons or excited atoms. And so we generalize it to get this equation of motion, which is all based on the equation of motion for the ground state. And we can normalize, we're using the normalization factor, we can get the value for that. And so the probability of state n being occupied is given by this function. And then more importantly, we get the mean chaotic photon number, which is this, which is just a ratio of the all total excited state occupancy over this ratio, I guess. And going back to chaotic photon number, this is a bit of a new term. I've never heard people talk about chaotic light, so I had to do some research to figure out what that was. So chaotic light is just photons occupying the diagonal in our density matrix. So it's observable values, and they are non-imaginary. It should say coherent light. That's what the word is blocked. But coherent light is going to be occupying the off diagonals. So there's going to be imaginary parts. So we can think about it as, if we think about the labs that we did, the coherency terms were occupied during transitions. So we can think about this light as transitory light. And back to the magnet analogy, which I'll talk about again in just a moment, we consider everything as a single electronic mode where everything is combining into a total wave function, but each particle contributes its own wave function. So yeah, we consider it just one whole wave function. And this figure is just describing how if we have some kind of pumping that we do at the beginning. So if we start here, we start at a higher ratio of ground state to excited state. Over time, we decay back to a standard. And so if we have fixed atomic populations, we'll always go back to our equilibrium. So in our quantum model, as Stephen set me up for, we do the analogy to magnetization. As we talked about, in magnetization, we have a bunch of particles that all interact with each other based on their dipoles. And we have temperature, which is analogous to population inversion. And since each of these dipoles interacts and affects each other's dipoles, so they're all coupled, this is very similar to electric field and a laser. So we can model electric field in the same way to magnetization. So we use the self-consistent field method, or I think it's also called Hartree-Fock, which is where we just take each individual particle, calculate a 1 electron wave function for just that one particle, imagining it's not interacting with anything else. And then we do a Slater determinant of all these wave functions to get one total wave function, which is based on all these 1 electron systems. And then we plug that into or use that determinant with a multi-electron Hamiltonian and get a decent approximation for the actual values here. And so using this method, we get the probability density for magnetization, which is this function, which is very similar to the probability density for electric field. It's identical in form. And so in this function, instead of using magnetization energy, we have free energy from our electric field, which is G, given by this long function. And instead of over KBT, we have K sigma, where I said sigma is our population inversion, and then K is just a factor of the gain, and N is the number of atoms. So another system I wanted to mention is just the 4-state system, because this is a 3-state and 4-state systems are essential for most laser operations. What's nice about the 4-state system is that we have enhanced lifetime because of a intersystem crossing. And so we have decay rates that we have to model for. And so we can have our population. This should be rho EE, one mistake just based on typographical errors, I guess. But so rho EE is modeled by the pumping rate, spontaneous decay, and Rabi oscillations. And our ground state is also like this, but more focused on the excited state. And so population inversion is just going to be the difference between our excited state occupancy and the ground state. What's really important from this function is this ratio 1 over gamma and 1 over gamma G. So gamma is the decay from our second excited state back down to its second ground state. And then gamma G is from ground back to original ground. And so if our lifetime of this excited state is greater than the decay rate from here, we can have a population inversion over time as our pumping is doing more work than the decay is. And then we can quantify the polarization, which will indicate how strong our electric field is over the cavity of our laser. And we also include B, which is our saturation, as Stephen mentioned earlier. And that's all I have to talk about.
Okay. It looks like you are the champion of one of the champions in being.
Okay, so today I'll be focusing on the Langevin equation and the Fokker-Planck equation. So a tiny bit of background. So both of these equations are based off of a process of stochastics, thank you, where Brownian motion is the most simplest version. So it's pretty much a heavy particle of mass and velocity that is moving in a liquid consisting of light particles. This is known as the Brownian particle. And then this particle is subject to random collisions with the molecules of the liquid itself. And then this gives rise to an average frictional force on the massive particle known as the, what was the word again? Stochastic force known as Ft that fluctuates around an average value. This is very important in the first equation of the Langevin equation because this information is actually used to make the equation itself. So under that stochastic force conditions, the Newtonian equation of motion becomes the Langevin equation, which is given here, where this is the stochastic force that I talked about on the last slide, M is mass, V is velocity, and then the fancy C in this case is a coefficient describing the friction between the particle and the bath. So
First term is frictional force,
I'm sorry.
Your first term is frictional force or different force? What kind of force is the first term?
You have stochastic force F, but your first term in this after equation equal sign. Does it include friction?
Is this frictional force or viscous force or what kind of force?
In other words, your energy is conserved or not? Because if you have friction, the energy is not preserved in the system. You have dissipation to the surroundings. So that's why it's important. Is your equation, Newton's equation, preserve the energy? So means frictionless forces or not preserved?
So dissipation does come into effect later, so that makes me believe that.
Yes, what would be the alternatives? What other characteristics could be assigned to the random force?
Some frictional force.
But are there any other ways to describe the random force?
Yeah, you can have frictionless
Can random force not friction?
Oh.
Can you have an example? Or your equation is only symmetric?
For the model, you can neglect the friction. In the reality, you of course have friction, but for the model, you can just neglect the friction. It's possible.
But Dinesh is asking about F, the random force.
I'm asking your first force, first term.
The first form is just mass times velocity.
So maybe
I think he's talking about the first one on the right side of
Yes,
the space,
yes,
the
that's
MC.
okay.
Information about friction should be in the after the equal sign, right?
So this Greek letter Z is friction.
It's friction.
That's Z, not C.
C, like the hair looking one, that's a capital version. of that.
We can argue for another 4 hours.
Okay.
I thought it was the colligative C. Okay.
Pronounce it.
Analog of English C. So
Okay.
Just to act like
What? Your question, time derivative of velocity and acceleration.
the what?
Time derivative of velocity and acceleration.
Yes, but that's not time derivative of velocity. No, I mean the second one.
Because that's.
Second one's just
As a what?
Drag force,
The
drag,
drag.
yeah, of like your particle moving through fluid and getting bumps from all different directions and stuff.
So it's mass times velocity.
What's it?
That term velocity is friction.
Yeah, basically.
Thank you for provoking intense discussion.
I guess the question was how to connect the first term after the equation to the force. So we have momentum MV, right? And then some strange letter which stays for friction.
Yeah.
And again, you probably can Google this in physics. So overall, it gives you the force.
Okay, so this is the very generalized version of this equation. So this is pretty much the beginning equation, but depending on how you swap things out in this equation will give you different end equations. So in that process of putting stuff in, switching it to try to get it relative to your specific case, you come with this correlation time, tau c, which denotes the time which the fluctuations of ft remain correlated. So this is the amplitude of the randomness happening in ft. So tau c is in between these two. So this is where between this and this, those fluctuations remain correlated to each other. And that is used later in when you do all the math to figure out the end equation that you're looking for. And then with this equation, it is safe to assume a few things. So the random force is equally likely to push in one direction as it is in the other direction. So the average overall realizations of the force is 0. So that's where we can make this assumption. And then also the random force exhibits no time correlation
but has a coefficient G in this case, which is a measure of strength of the mean square deviation of the stochastic force. So yeah, so I did not give an out equation just because there are so many, but you can correlate the Langevin equation to my next equation, which I will talk a little bit more detail later. But for the Fokker-Planck equation, again, this top one is the more generalized one, just like the last one, depending on what you are particularly looking for, it changes at the end. So on this one, I will go over two different final variations of the Fokker-Planck equation. So as talked about in the other laser classes, we already know what C is, and then alpha and alpha star in this case is alpha is the annihilation operator and alpha dagger is the creation operator. And then this term right here is actually the I'm thinking on the word. The P representation, which is also known as the coherent state representation. So this is what that equals, where this is the average mean. And then D is...
Intervene. So no question, I just make a comment so that we develop slowly but surely. So the first line that Tori has introduced is an equation in partial derivatives, right? So instead of this dot, there are derivatives over alpha, first and second order, and derivative over time. So it is something that develops in time and some space. So it is distribution as function of alpha and alpha star. Tori correctly mentioned that alpha and alpha star relate to creation and annihilation operator, but to be more precise, it deals with amplitude of coherent state, with eigenstate of annihilation operator. And the amplitude of annihilation operator is equivalent to is proportional to the strength of electric field. So in some sense, the distribution that Tori is describing is how probable is to find that electric field has so large strength at a certain time. And then she's going from declared partial derivative equation to its solution. So there are two independent space variables, one time, and here solution is oscillating Gaussian. Oscillating two-dimensional Gaussian, like Patricia was doing her projects. Okay, sorry for the interruption. Please continue.
I guess I forgot to mention that this is one of the solutions with a whole bunch of math. There's multiple pages of it, so with the limited amount of time we have, I didn't want to get into that. But the D is the dispersion of the Gaussian function about the mean value, like I said earlier, is this. Okay. So we have a function, well, we have an equation now, and this is the figure that goes with the equation. So this 3D part, as we can see, is that Gaussian distribution that we are used to, just in a 3D format. So at the beginning, at initial time, which is kind of hidden by this, but this is initial time of the P representation. The entire equation starts here, where D is at the initial value of 0. So currently there is no dispersion of the Gaussian function whatsoever. So if time were to stay stagnant, it would just go around this dark black circle. And then once we actually start getting into time, we get away from that excited state and start going back to the ground state. And during this, we have the dampening effect that occurs causing it, where the average value, so the dampening is pretty much here, will start oscillating slowly into a spiral until it gets to 0.
How should we interpret your axes, the imaginary alpha and the real alpha here?
So Stephen explained the imaginary and real, but this entire thing is in a pure coherent state of ket alpha. So I'm assuming that's where the imaginary alpha and real alpha come from. And this is the coherent state that the entirety is in. Does that answer your question?
Do you want to give her time to Tori, or you want to ask?
I'm fine with either.
So real and imaginary parts of alpha will be proportional to electric field amplitude and to derivative of it. And in this sense, this phase diagram is very similar to what one does in classical mechanics for position and momentum, also going in circles. But since it is damped, instead of going in circles, it goes by spirals, ends up in the center. You're satisfied? Sorry, you're okay. Just continue.
Trying to think if there's anything else for this image.
So why does it peak up in the Z dimension just like toward the end? Of this, I would say by the end of this decade, like why is that peaking up much more in the Z dimension versus like earlier on?
Can you talk about this part?
The peak is moving entirely through space with respect to time.
Oh, so
the dot line is tracing the path.
okay.
So this is just showing it mid, this entire 3D part would start here and just slowly move around.
Okay.
Sorry, so does the center of, based on my understanding, like what I'm understanding, so does the center of this means that that's the ground state?
The center, so when this gets to here,
Yes.
yes, that would mean that it's back in the ground state. Yep, because when it's here, it's in the excited state, and then it slowly makes its
So
way.
like the first ground state Gaussian function, like that looks like the ground state Gaussian. Is that why you give that shape?
It's like, yes, sorry.
So at zero temperature, it would relax the ground state of the oscillator. But if the temperature is above zero, then it will increase the width. So for thermal state, it also centers at the equilibrium point, but the width is broader than for a Gaussian for the ground state.
Right.
Does the angular momentum vary with time?
No angular momentum. If one wants to apply to classical or to any harmonic oscillator in terms of position and momentum, then it's linear momentum. Position and momentum, they make a circle in a phase space, not in a real space. In a real space, position oscillates like cosine and momentum oscillates like sine. And if you do parametric plot, it will be a circle. But there is no momentum, it's linear oscillator in motion. Does that answer your question?
Okay, so like I mentioned earlier, that the Langevin equation can be used as well. So the P representation also helps with the correspondence between the density matrix and the Langevin equation through the equation of motion of the P representation. So this is the final result. So pretty much there was a whole bunch of math.
Intervene and do like a little, how to say, comment, editorial comment. So Tori is telling everything correctly, but additional comments so that we stay on the same plane or same page. In previous couple of slides, she was given an equation and solution, right? And equation and solution were corresponding to the limit only when one has the losses introduced to us by Hadassah. Then there is a version of the same equation in case if there are gains, if there is a pumping. In case with pumping, of the mode of the oscillator of the resonator mode, equation would take the whole page just to write down, and therefore she's skipping the equation. Then Tori is introducing to us the solution of Fokker-Planck equation with both gains and losses. And there is one more comment. Before we had a nice picture with spiral, because it is quite predictable what system does if it is created in the excited state and then it slowly goes to ground. But if you have a pump and you wait long enough, it will very quickly arrive to the saturation regime, and then it will move there randomly and we will not remember what is the phase. So it will perform some steady state solution, which time component will be just regular oscillations with a given frequency. And Tori is skipping all these details and provides us only steady state solution for the Fokker-Planck equation in the limit of both pump and down. Okay, please continue.
Okay, so this is the end equation, like I said earlier, where A, like we said before, is the linear gain coefficient, and B is the, there it is, B is the self-saturation coefficient, and then N is actually the normalization constant. So near the threshold, the steady state solution of the equation of motion, which is this, RA here is also a constant, right? But so that's the linear motion when you're near the threshold. And then the figure is the phase diffusion model of the laser line width, which is what this equation helps. Well, the line width helps with this equation. So it pretty much helps you find the solution for the equation when you actually go to solve it and put in all your values and stuff. So this is the electromagnetic field as a complex vector. And then with experiences of small changes in phase due to the spontaneous emission events that are occurring, these changes are totally random, so there's no way to know exactly where it is. That's why all these dots, there's no pretty much rhyme or reason besides them going in the 2-pi sphere. But the phases gradually diffuse and becomes equally distributed over all of the 2-pis, which is why you can kind of see that sphere-like thing, even though this is supposed to be totally randomized. There is an average of them all. And then it is assumed that the laser is operating sufficiently far enough above the threshold that the amplitude fluctuations can be ignored for this one, unlike with the other one where we had to apply the amplitude and what made it have that spiral.